All right, hey everyone. Welcome back to our series on linear algebra. So today we'll be tackling section 5.2, which is orthogonal complements and orthogonal projections. So, uh, no, these are all interesting words. Um, the idea behind an orthogonal complement is a generalization of the concept of a normal vector to a plane. Let's review that concept for those of you who haven't seen it before. So the plane, we're just going to use this example. X plus 2y minus 2z equals 0. Notice that's a plane in R3 containing the origin. It is the set of vectors in R3 satisfying that equation, whose coordinates satisfy that equation. But we can also go and solve some system of equations, homogeneous, that. And you'll find that there are two free variables. And so the dimension of the subspace is 2. Whatever. Give a parameterization of the plane. It'll be all the vectors of the form any number for s, any number for t. And then how do you get the third component? Well, you take half of the first component plus the second component. And so I've just decided to write that as this basis, 2, 0, 1, and 0, 1, 1. So, and this is a standard procedure, right? We've found a basis for a two-dimensional subspace before. What's interesting is that the subspace has a plane in R3 has a normal vector, and to get the normal vector, just take the equation defining that plane, so x plus 2y minus 2z, and extract the coefficients on x, y, and z. So 1, 2, and negative 2. That gives us this normal vector. Normal, meaning in this case, this is terrible because we've already used the word normal several times. But in this case, normal does not mean length 1, it means normal to the plane. In other words, sprouting out perpendicular to every vector contained inside the plane. So in other words, if you take the dot product of your normal vector, which I'm calling n, and any vector inside this plane, you should get precisely 0. I've done the two basis vectors here, and you can verify these dot products, but let's just do it for literally any vector in the plane. So any vector has the form st s over 2 plus t. Dot that with 1, 2, negative 2, and you'll get in the first, you'll get dot product, right? So we have to multiply component-wise and then add. So s plus 2t minus s minus 2t, which is precisely 0. Notice, any vector in the plane, dot product with this one vector, and you get 0. As a picture, it looks something like this, right? N, the normal vector, is somehow sprouting out of the plane, perpendicular to every vector w inside the plane. This is the best drawing I could do. I think it's decent. And so we're looking at, right, some vector that has that property. So the question is, can we generalize this to higher dimensions? What are the important properties satisfied by the subspaces and vectors in question, right? Well, notice if you take the span of n as whatever line that it spans, that is a subspace of R3, where every vector in that subspace is orthogonal to every vector in W, the plane. And so the question is, the general question that we're trying to answer is, can we find two subspaces such that every vector inside of one is orthogonal to every vector inside the other one? That's what we're after. And we give a name to two subspaces that satisfy that property, we call them orthogonal complements to one another. So, okay, here's the actual definition. Let W be some subspace of Rn, a plane in R3 or a three-dimensional linear space inside of R12. I don't know, just some subspace. Okay, a vector V is orthogonal to the subspace W if V dot W is 0 for every single W in that subspace. Okay, and now the set of all vectors which are the set of all vectors that are orthogonal to the subspace W is called the orthogonal complement of W. Again, in our previous example, it was the set of all vectors that were orthogonal to the plane W. That would be just any multiple of n. Okay, so that set of vectors is called W, the orthogonal complement of W, denoted with W and then, what is that, an upside down T? No, you remember perpendicular? The perpendicular symbol? You have like L is perpendicular to M for lines L and M from geometry. Anyway, okay, the left, we call it W perp. We just say the orthogonal complement of W is W perp. That's how we say this word, or this symbol is what it is, I guess. Upside down T, yeah. Okay, let's look at an example. The example that we're keeping fresh in our minds is if L is the subspace, which is the span of the normal vector n, and Pn is the normal vector to a plane containing the origin, then L is W perp. But more importantly, every vector in W is perpendicular to a vector inside of L. Right? Sorry, every vector in W, in W is perpendicular to a vector inside of L, which means W is L perp, the orthogonal complement of that, whatever that line was. What is its orthogonal complement? Well, it's the entire plane W. Except I don't know what P is. Should be W. Okay, great. Good. Okay, so let's turn that into some good theorem properties of orthogonal complements. Okay, so start with any subspace of Rn. That right off the bat, the orthogonal complement of W is a subspace of Rn. It is also a subspace. It is the span of some vectors. And then, of course, if you were suspecting this, you're right. The orthogonal complement of the orthogonal complement, or W perp perp, is just back to W. So, yeah. Okay. Here's something that's interesting. Property 3. If you take a vector space, a subspace, and intersect with its orthogonal complement, that is, what vectors are common to both subspaces, there is only ever one, and it's the 0 vector. Because the 0 vector, if you dot product with any vector, gives you 0. But also these subspaces will only, like, they're never going to be like meeting, right? So for example, how can a plane meet a line? Well, they can either meet transversely, so the line pierces the plane, or the plane contains the line. That will never happen, which means that the only way that these things will meet is if the line pierces the plane, or if they intersect transversely. But more than that, it's not like they're going to intersect anywhere outside of 0, because you need something that's orthogonal to every vector inside of each one. So the 0 vector is the only one that does that, and they will meet. So notice this is not like the 0 vector or the empty set. No, they are going to meet at 0, because 0 is orthogonal to everything, right? And so it's precise. The intersection of W and W perp is precisely 0 every time. Okay, and then if we have a basis for W, so say little w1 up through wk, then V is in W perp, the orthogonal complement, if and only if it's the dot product of V with every basis vector is precisely 0. So you don't have to check that V is orthogonal to every vector inside of W, just every basis vector given some basis. Most proofs for each of these parts of the theorem amount to just like fact checking or definition chasing, so we're gonna not cover them. But we'll look at some a very specific case where orthogonal complement arises. And that would be in the relationships between the row spaces, column spaces, and null spaces of a matrix. So, and if you've been suspicious that row space, column space, and null space are all related subspaces given some matrix, you are on the right track. So first of all, we have let A be an M by N matrix, so not necessarily square. Then we have the orthogonal complement of the row space of A is exactly the null space of A. That's the one that we're going to spend the most time proving. But also, notice that the other part of the theorem says that the orthogonal complement of the column space of A is just the null space of A transpose. That's actually just a restatement of the first one with one additional fact about row space. The column space of the transpose is the row space of the original, or whatever. The column space of the transpose is. I said the same thing twice. Okay, we'll see it show up in the proof. Okay. So the proof goes like this. The proof is what is the orthogonal complement of the row space of A? That is the set of vectors whose dot product with every row of A. I'll write the set of vectors V in Rn. N because we have to have a column with as many a column vector with as many entries as there are columns in A, which is N, right? So the set of all column vectors V in Rn such that V dot row I of A is 0. In other words, a vector inside of the orthogonal complement of the row space of A satisfies the property that the dot product of that vector with every row of A is exactly 0. Then A dot V for every single one of these vectors is the 0 vector. Yeah, just dot with each row. Like, what is this multiplication? Just take the column vector, turn it sideways, multiply it by every row, add components. This property guarantees that every time you do that, you're going to get 0. So the output of every dot product is 0. So the output of the matrix multiplication is the 0 vector. Wait a second, I took a matrix and multiplied it by a vector and got the 0 vector. The vector is inside the null space. Yeah. In fact, that's the definition of the null space. Every vector in the null space satisfies exactly this property. So the answer is the null space of A. To show the second part, okay, now we have to state it carefully. The column space of A is exactly the row space of A transpose. If I want to compute the orthogonal complement of these things? Well, in other words, if I want to compute the column space, the orthogonal complement of the column space of A, I just compute the orthogonal complement of the row space of A transpose. Mouthful. But that's just the null space of A transpose. And so we're done. Pretty nice. It was that fact that the column space of A is the row space of A transpose that I was trying to say and just couldn't get it out. Okay. This gives rise to a concept called the four fundamental subspaces of a matrix. Specifically, take your matrix A, so A is an m by n matrix, view it as a linear transformation from Rn to Rm. And just if you're worried about that, see section 3.6 where we introduced linear transformations. The number of rows and columns match up in terms of inputs and outputs. Remember, just now we took an n vector, or a vector in Rn, and multiplied it by A in order to get a vector in Rm, which was the zero vector in our case. But right, you just have to make sure that your dimensions are matching up. Okay, so there are four fundamental subspaces of the matrix corresponding to this linear transformation. Okay, two of them are subspaces of Rn, which are orthogonal complements to one another. The other two are orthogonal complements in Rm. Okay, there it is, row space of A and the null space of A. Those are orthogonal complements in Rn. And then the column space of A and the null space of A transpose are orthogonal complements in Rm. Notice that the row space of A is some subspace inside of Rn, whereas the null space is the orthogonal space to the row space, but it's also the subspace of Rn that gets sent to zero under the linear transformation. So it's the part that gets collapsed, which means that the row space, what does that correspond to as a subspace? We haven't really answered that question, but it's the subspace of Rn that does not get collapsed under the linear transformation Ta. The column space, we have talked about what that means kind of geometrically, but viewing Ta as a linear transformation, the column space of A is the range. It's the set of vectors inside of Rm that get hit by some vector inside of Rm under this linear transformation. That's not necessarily all of Rm. Remember, linear transformation goes from a domain Rn to a codomain Rm, but it doesn't necessarily hit every vector inside of the codomain. A set of vectors that it hits is just it's called the range, right? And you remember this from learning about domain and range in like algebra class or something. The range is the set of things that get hit by your function or whatever, and it's not necessarily the entire codomain, right? That's what the column space of A is measuring. It's the range of the linear transformation. And then the null space of A transpose is this weird thing that shows up as the orthogonal complement of the range inside of the codomain. Yeah, that's exactly right. So, and so this makes for, we call these the four fundamental subspaces of a linear transformation or of a matrix. Okay, so let's go and do it for a hard problem. We're not going to do it. Okay, we know how to do this already. We know how to find the four. Okay, we just didn't know that they were called the four fundamental subspaces, but it turns out that's what they are. So find bases for the four fundamental subspaces of this 4x5 matrix. Okay, so this is a linear transformation from R5 to R4. Okay, now, we can view it, right? This is the matrix corresponding to the matrix transformation from R5 to R4. Now, We already know how to find row A, null A, and col A. So I'm not going to do them here. But right, for row A, we row reduce the matrix and then figure out how many linearly independent rows we have. Whichever rows don't reduce to zero become a basis for the row space. After row reducing, we have some row reduced matrix. Just augment with the zero matrix or the zero vector and solve, the corresponding homogeneous system of equations for, so just find all solutions and parameterize the subspace of solutions. That is precisely the null space. The number of free variables is the nullity, which is the dimension of the null space. The rank is the dimension of the row space. Okay, for the column space, what you do is look at the reduced row echelon form of your matrix A, go to the original matrix, and circle whichever columns show up. Oh, I guess I should tell you what the reduced row echelon form of this matrix is. Let me just do that real quick. You can see it right here, but it's nice to be able to refer to it. It's 1 0 1 0 negative 1 0 1 2 0 3 0 0 0 1 4 and then 0 0 0 0 0. Okay. This is the reduced row echelon form of A. So what we do for the column space, right, is we look at whatever columns have leading ones in them, and then go to the original matrix and circle those columns. Those are a basis for your column space. And now what's left is to compute the null space of A transpose. Okay, so I guess we can do that too. Okay, so the null space of A transpose, we have to row reduce A transpose. I'm gonna just tell you what that is. The row reduced echelon form of A transpose, mostly because what are we going to do? Transpose the matrix and then row reduce it. Okay. 1 0 0 0 0. Notice this is going to be a 5 by 4 matrix now. 0 1 0 0 0 0 0 1 0 0 and 1 6 3 0 0. Okay. Now we have to go and compute. We have to augment with the zero matrix. So let me just go ahead and do that. And then notice that this is a homogeneous system of equations. This is the coefficient matrix for it. We can go and solve that system. So x4 is free. Remember, this is solutions. This is a system with 5 equations and 4 unknowns. Okay, x4 is a free variable. And then x1, x2, and x3 all depend on x4. So the null space of A transpose is the span of a single vector, namely -1, -6, -3, 1. Okay, just standard procedure, but technically we haven't seen that one done yet. You have to transpose the matrix before computing the null space, as difficult as that might be. Okay, great. So now we have a different type of problem, which is let's just go and find a basis for the orthogonal complement of some matrix. Of some subspace. So they hand you a subspace. This is a 3-dimensional subspace of R5, which should be terrifyingly reminiscent of something that you'll see on the homework, the written homework this week. Three-dimensional subspace of R5, and it's the span of these three vectors. Go and find a basis for the orthogonal complement. Fortunately, if we're looking at W is like, let's just like back out a little bit. W is the span of these three vectors, which means we're assuming that these vectors are linearly independent. You can verify that with a quick inspection. Okay, and now if W is the span of these three column vectors, then W is precisely the column space of A, where A is like, oh, I don't know, where A has columns. Basis vectors of W. It probably would have been easier to just label these vectors W1, W2, and W3, and then just say A is the matrix W1, whose columns are W1, W2, W3, whatever. Okay, but the point is, W is the column space of the matrix. We need to find its orthogonal complement. Well, W perp is just the null space of A transpose. Some 5x3 matrix. 3x5 matrix. Let's write it down. Okay. 1, -3, 5, 0, 5, -1, 1, 2, -2, 3, 0, -1, 4, -1, 5. Take that, augment with the 0 vector, row reduce. The book works this out for us, thankfully, but okay. On an exam or on the homework, you just row reduce. We're going to end up with two free variables. Two free variables. The last two columns will be 3, 1, 0 and 4, 3, 2. And so W perp is the span. And hopefully you guys can read the solution off of this equation. It's the span, it's the set of vectors of the form. You know, if S is the free variable here and T is the free variable there, then x1 is just negative 3s minus 4t. X2 is negative s minus 3t. And x3 is 0s minus 2t. And so for a basis, we just write down, you just split apart the s and the t's. So this is the span of the basis, -3, -1, 0. Oh, st1. Okay, I definitely, we need 5 components in our vectors, but like x4 is s and x5 is t. I forgot to write those. So let's make some space in our vector. This is awkward. Like that. Okay, and then, right, because we're looking at a subspace of R5. That's, yeah. W perp is a subspace of R5, not R3. So -3, -1, 0, 1, 0. And -4, -3, -2, 0, 1. Okay. Notice you have to, one way that you can check that this is honestly the null space, take these vectors and dot and multiply them by A transpose. You should get 0. Okay. So that was the discussion surrounding orthogonal complements. There is a related topic, orthogonal projections, which is going to be a tool that we use moving forward. Again, projections are going to be very, very useful when talking about orthogonal bases, orthonormal, this, that, Gram-Schmidt. We haven't talked about Gram-Schmidt orthogonalization, but we will. And being able to project one vector onto another is going to be super useful. So we did not talk about this in chapter 1. We glossed over it briefly, but in case, I was going to put recall here. That's not right. It's not a recall. I'm just going to give you the definition. So proj UV. It's the word proj, and then a subscript of u, and then in parentheses v. This is crazy, bizarre notation. Is the projection of v onto u. I view this as a function that takes in a vector v and outputs a vector inside the subspace, which is the span of u. In other words, just take u. Here's u. Span it outward. Take some vector v, any vector v, and then just take the part of v that lives along u. That little vector right there. Okay, that's confusing, too many arrows. Whatever it is, I'll just draw in a different color, is proj u of v. Okay. So that, and by the way, the name for that little blue vector is the projection of v onto u. If you then do v minus that vector, by vector subtraction, you'll get precisely this vector, which is the component of v, which is orthogonal to u. Notice that vector dot with u, they're going to give you 0 because they form a right angle. Okay. That's okay. It's called perp uv. It's the component of v orthogonal to u or perpendicular to u. You can call it the perpendicular component of v, but you have to make sure perpendicular to what? To u. Notice it was obtained through vector subtraction. So if you just add proj uv to both sides, you can write v as proj uv plus perp uv. And more importantly, proj uv and perp uv are orthogonal to one another. So if w is the span of this of u, like we wrote, and little w is proj uv, and little w with a perp is perp uv, then v, this is just restating it, v is w plus w perp, little w, lowercase w's all around. That's why I've been putting little serifs on my capital W's. God forbid you get those confused. One is a subspace, one is a vector inside that subspace. Okay, right. We call this the orthogonal decomposition. And so, but first we have to generalize. So we would love to be able to do this in general for 2 orthogonal subspaces or 2 orthogonal complements, sorry. But we have to generalize the notion of orthogonal projection and components that are orthogonal to a subspace. So let's just do that real quick. That's just a gnarly definition, as we start with every time. So start with W is any subspace of Rn, and equip W with an orthogonal basis, and we're calling that one U1 up through UK. Then for any vector v inside of Rn, the orthogonal projection of v onto the subspace W, you do it like this. First of all, it's denoted proj capital W of v. And the way that you do it, don't worry about this business. I glossed over that in our previous definition. I'll mention it briefly in a moment. But for now, really what you should think about is do proj ui of v. In other words, project v onto each of the ui basis vectors for W. Okay? Whatever that's a bunch of these little blue arrows. You're computing them, and then you just add those vectors together to get the projection of v onto W. What is the middle box? The middle box is the formula. It is literally a way to compute what that little vector is, and it's just take ui.v, divide it by ui itself, and then multiply by ui. So I don't want to dwell on that. It's mostly just a computational tool. Although if you really like the geometry, you may want to look into it. Okay, and then by the way, if you want the component of v that's orthogonal to that subspace W, that's just perp capital W of v, and it's just v minus proj WV. So there's no difference in that definition at all. You just do v minus the other one. Okay, let's do an example for it. So x is going to be the plane, W is the plane in R3 whose equation is x plus 2y minus 2z equals 0. Remember we had the basis for W. Which, from memory, I don't know if I can do this. I believe it was 201. And 1, 0 minus 1. 0, 1 minus 1. Probably. I believe it. I mean, those two vectors are linearly independent, and the components both satisfy that equation. So this is a basis for the subspace. Okay, great. I just want to make sure that we're not missing anything. So now what we want to do did we find an orthogonal basis? This basis is not orthogonal. Okay. Right. All right. This basis is not orthogonal. Right. We had to go and so the problem here is that this basis is not orthogonal, which we need for our definition. That's okay. We saw last time there was a procedure to find an orthogonal basis given some regular basis. It's brute force, and we are going to use it here for the last time. And then in the next section, we'll tackle the issue of this seems to be a problem. Given some random basis, can I get an orthogonal basis, please? Okay, but for now, what do we need? Okay, I want a vector, let's say orthogonal to this guy. Actually, let's make it orthogonal to this one. I feel like that's going to be easier because ones and negative ones. Okay, which is also inside of W. So if you're inside of W, a vector inside of, I'll just call it ABC, I guess. Inside of W, satisfies a plus 2b minus 2c equals 0, of course. But if you're orthogonal to this other guy, you also have, a, if you like dot these two vectors, then you have a times 0 plus b times 1 plus c times negative 1 equals 0. So b equals c. Or b minus c equals 0, we'll say. Okay? That's interesting. So now we'll just go and, so there's a homogeneous system. 1, 2 minus 2, 0, 1 minus 1, augment 0, 0. We have to solve this. Row reduce it. I dare you. You'll just end up with 1, 0, 0, 1, 0, minus 1. We have a free variable z, like c. I have the x3, whatever. The third one is a free variable. And notice the first equation implies that x1 equals 0. So, and the second equation implies that, like I was saying, b equals c. So 0, c, c. Let's do 0, 1, 1. That seems really lame. 0, 1, 1. C equals 1. Okay. Is orthogonal to 0, 1, negative 1, and is inside of W. So we rewrite W as the span of 0, 1, negative 1, and 0, 1, 1. It's kind of lame. I think this is like a YZ plane or something. Maybe not. Anyway. Okay, and so now, moving forward, so what do we have? So now we have an orthogonal basis. Compute proj onto W of, what are we trying to do? Of 1, 2, 3. 1, 2, 3 projected onto W. We can do that. We just take, so it's the sum from I equals 1 to 2, which is really dumb. I'm just reading this off of the formula of proj. Oh, okay. Of let's call this U1 and U2. That way we're not crazy. Proj UI of V, which is, I'm just going to write it out without the big gigantic sigma. Proj U1 of V plus proj of U2 onto V. We have formulas for each of those. It's V dot U1 over U1 dot U1 times U1. That looks really silly. Notice it's the quotient of two numbers times a vector. Okay, plus V dot U2 over U2 dot U2 times U2. Okay, and now we have to compute V dot U1, V dot U2, U1 dot U1, and U2 dot U2. I'm gonna wait. Those are all dot products, so I'm just gonna do them without showing any work. V dot U1 is 1, 2, 3 dot 0, 1, -1. That's 2 minus 3, which is -1. U1 dot U1 is 2. V dot U2 is 2 plus 3, which is 5. U2 dot U2 is 2. And now we just do -1/2 U1 plus 5/2 U2, which is 0, -1/2, +1/2, plus 0, 5/2, 5/2. And so proj W of V is 0, 4/2, which is 2, and 6/2, which is 3. 0, 2, 3. And notice, if really W actually happens to be in disguise, apparently W is like the YZ plane or something. Seems strange. Then just projecting away from chopping off the first factor preserves the other two factors. So this is consistent. And now we want to find perp UV. Perp WV is just 1, 2, 3 minus 0, 2, 3 minus proj WV, which is just 1, 0, 0. That's the perpendicular component. As a bonus, I'm going to write the orthogonal decomposition of V, which we don't know what that is yet. I guess we do. Maybe. No, we haven't written it down yet. That's the next slide. Okay, that was a spoiler. Jeez. V is precisely 0, 2, 3, the component coming from W, and 1, 0, 0, the component coming from W perp. It doesn't always work out that it's just like these two separated like that. You might have some weird square roots or something showing up. These dot products and like a vector dot with itself might yield some nasty situations. But in this case, we're totally fine. Okay, so I keep calling this orthogonal decomposition of a vector. However, the orthogonal decomposition theorem says, in words, that the orthogonal decomposition of a vector given some subspace, or with respect to some subspace, is unique. So it goes like this. Let W, again, be any subspace of Rn, and let V be any vector in Rn. Then there are unique vectors, one inside of W and one inside of W perp, whose sum is precisely V. Unique vectors. To prove this is actually pretty intense. You have to show existence and uniqueness, and you have to appeal to the definition of the projection of V onto W, and then the perpendicular component of V to W. So that just involves a gnarly computation of arbitrary vectors. It's not really worth showing, although it is spelled out in the book, and the book does a very good job of saying it succinctly. So better than I would do. So I will leave that for you to read. Instead, I want to conclude by investigating one consequence of this theorem, which is that for every single subspace, which, by the way, this is something you would have suspected. For every subspace W of Rn, the sum of the dimensions of W and W perp, its orthogonal complement, is precisely n. Every time. With the plane and the line, 1 plus 2 is 3, and 2 plus 1 is 3. But in general, you take a vector. Oh, the rank nullity theorem is this, right? The rank is the dimension of the row space. The nullity is the dimension of the column space. Well, the nullity is the dimension of the null space. But from the theorem that we proved earlier, the orthogonal complement of the row space is the null space. And there we go. Their dimensions should sum up to n, right? That's what this one says. So let's actually prove this one. The proof is kind of fun. We just want to, so the proof is we're going to find a basis of Rn. So, given bases of these two things. So, let, I don't know, U1 all the way up to UK. And V1 all the way up to VL. Different letters, not necessarily the same. Be bases of W and W perp, respectively. In other words, U1 up through UK is a basis for W. V1 up through VL is a basis for W perp. I have no idea what K and L are, but obviously this means that the dimension, the dimension of W is equal to K, and the dimension of W perp is equal to L. Once again, I don't know what K and L are. I'm just saying, given some subspace W, it has some dimension. Call that dimension K. Given the subspace, and then given its orthogonal complement, W perp, that is a subspace by theorem, like whatever one we saw earlier. It has some dimension. Call that dimension L, right? What I want to show is that K plus L equals N. Okay, let B, fancy B, be the set U1, set of vectors U1 all the way up to UK, and V1, so it's the union of these two sets, all the way up to VK. Sorry, VL. I claim that B, fancy B here, is a basis for Rn. If it's a basis for Rn, I promise it has n vectors in it, because Rn is n-dimensional. Okay? I want to prove that it's a basis. So claim. There's no E in claim. What? B is a basis for Rn. I have to prove that it's a linearly independent spanning set. If I can do that, then it's a basis for Rn, and the number of elements in it is n. But notice the elements in it are just the elements inside of the bases of the other two, which are unique set, like they're distinct sets, because these two, like W and W perp, only intersect in the zero vector, but the zero vector can never be a basis vector. So so all I have to do is show that this is a linearly independent spanning set, and we're done. Linearly independent, let's go. Okay. Ui dot uj equals 0 if I is not equal to j. If and only if, technically. That is true for vi dot vj. Why? Because they're orthogonal bases. I didn't say that. Be orthogonal bases. Well, I mean, okay, great. Haha, I cheated. No, I just had to modify my assumption. Nothing changes in the assumption. It's just that these bases are orthogonal. And notice, if I didn't have orthogonal bases, that problem that we solved where we had to have the extra step at the beginning to make the bases orthogonal, was like, we needed that, right? We can do that here to fix the situation and then let the new basis be U1 and V1 and whatever. So, okay, yeah, be careful with our assumptions. Start with an orthogonal basis. Doesn't matter. So, in other words, as long as you're taking the dot product of UI and UI and UJ or VI and VJ, you get 0. But also, UI dot VJ. Why is that true? Like, the dot product of UI and VJ is equal to 0 for any I and any J. Any U vector dot any V vector is 0. Why? Because W and W perp are orthogonal complements. In other words, the dot product of any vector in W with any vector in W perp is precisely 0 every single time. That's the whole point of this lecture. So we get this guy, always. In other words, fancy B is an orthogonal set. Fancy B is an orthogonal set, a set of vectors that are all pairwise orthogonal. And then we have a theorem from the last lecture, 5.1, that says that, thus, B is linearly independent. How do we know that it spans? How do we know that it spans Rn? Basically, from the orthogonal decomposition theorem, every vector V. Okay, we'll just do it right. Let V be a vector in Rn. Okay. Then uniquely, V is equal to W plus W perp, where little w is a vector inside of W, and little w perp is a vector inside of W perp. Each of these has a unique expression in terms of the one in terms of the UIs and one in terms of the VIs. So their sum is a unique expression in terms of the elements of B. Can be uniquely expressed as a linear combination of vectors in B. But since V was chosen arbitrarily, V was any vector in Rn, we say thus span of B is Rn. So B is a linearly independent spanning set for Rn. So B is a basis for Rn. Every basis for Rn has precisely n elements. The elements of B are just the union of the elements of the bases for W and W perp, which have no common, which have no elements in common. So it's what we call the disjoint union of those two things. That means that whatever k there were k elements in one set and l elements in the other one, it follows that k plus l is equal to n. And so we're done. I think that's probably my favorite proof that we've done so far. It's a very airtight. So great. Okay, so that's enough for this video. By the way, the rank nullity theorem is a consequence of this, and also there's a upgrade to the rank nullity theorem too. Not upgrade. It's just there's an m by n k or n by m whatever n by whatever. I'm not going to say it again. Example where version of the rank nullity theorem that comes out of this as well. If you just trace through column space and null space of the transpose, the other two fundamental matrices, but fundamental subspaces of the matrix A. So next time we'll talk about the Gram-Schmidt process and the QR factorization, and that will be the last thing that we do in chapter 5. So I will see you in the next video.